Let's go ahead and get started, and we will start with group 3 today. I'll give the rest of your group a few minutes to show up, and who knows, buses, things like that. It happens, it's whatever, it's fine. Happy Valentine's Day. So what better way than to show your love for CPRE 480 than via demo day and via talking about your designs. I took a preview, took a look at the slides. It looks like a lot of the groups, you did get things working. One thing I do think you have to watch out for a little bit with these labs, starting really now, going from MP1 to MP2, it's a small gotcha, is that I think it's pretty easy to build up small amounts of like technical debt along the way, right? You know the general concept, right? Where you're working on something for a period of weeks, and you kind of put off doing some final little bit of either adding features or documenting what you've done or understanding what you've done or fixing the last couple of bugs that probably still need to get fixed because the result has been good enough along the way, right? And so we kind of just slowly accrue that technical debt that eventually becomes an issue. And you may wind up seeing that in MP2. So for MP2, it is this very kind of hyper-focused thing that we are doing in working at rasterization algorithms for MP2. But some small bugs that you may have had in MP1 may not at all be apparent until you try to run the applications from MP2, in part due to the nature of what we have in MP1 versus MP2. In MP1, there's a balance between the amount of pixels on the screen and the amount of points that we're specifying. For every point we want on the screen, we specify a GL point for it. That can sometimes hide some bugs that you may not realize are there, either in the driver or in the hardware, or how you're interfacing with cache and things like that, or going from frame to frame. Now in MP2, that's not going to be the case. You're going to be specifying just 3 vertices, and it's going to be a red triangle that fills the entire screen. And so for those 3 little vertices, there's a whole lot of work that your pipeline now has to do, the whole bunch of fragments that your pipeline now has to generate. Your render output's a lot busier. And that may expose some bugs that you didn't see in MP1. So I guess my perspective here is not to get discouraged when that happens. I think that's just going to naturally happen here. One solution I think to that is to make sure you have a pretty decent understanding of why your MP1 design works the way it does. It's okay when a deadline comes, okay, we got to work. We got the green triangle on the screen, we're done. I understand that, and that's okay. But now when it comes to really debugging, when something no longer is working, you have to kind of go back and try to really understand how is the data flowing through the system, how is the application interacting with the driver, interacting with the hardware, and making sure that you understand that at a good enough level to realize, okay, we're actually not doing this part exactly correctly, and we didn't see that bug in MP1 for this particular reason or the other. And I think that's why MP2 is a little bit more challenging than MP1. In a sense, it'll be very similar. You're building another IP core, and you're interfacing with AxiStream interface, and there's a driver interface for it as well. All that stuff is very similar feeling, but it's going to expose, I think, more perhaps old bugs you may have from your MP1 design. How is your group 2 membership attendance now in good enough shape to get us going, I think, for today? That's not bad. That's passing. We'll take it. Here, as you know, the template for today, 12 minutes is going to be sufficient, but take your time and talk about it. I may, speak up every so often and have questions or suggestions or point out where there may be a bug here or there along the way. And I may push a little bit more today because I think we have time to do that. And then the final reminder is MP2, I think kind of like MP1, if you haven't done the pre-lab before you come to lab tomorrow, it's not going to make a ton of sense. At the very least, read through the MP2 assignment, look at the pre-lab for it, work it's pencil and paper again, the pre-lab for MP2, work your way through it, make sure you conceptually understand what's happening there. There is a lot of, we'll call it very basic like algebra in doing rasterization. So there's mathematical ways we have to determine if this is red and this is blue, how do we get reddish blue as a gradient along the way? And how do we do it with as little arithmetic units as possible, essentially? You read through MP2. It's okay if you don't perfectly 100% understand it, but put in a good faith attempt at the pre-lab in advance of tomorrow's lab. So having said that, as always, this is my favorite day in the semester. I just kind of get to sit. You guys get to kind of come up and do your best, okay? And of course, if anyone has questions as you go, please feel free to jump in as well. I'll sit up here so my audio picks up on this. And before you even get started, as you are scattered for maximum distance here, the person who's talking probably needs to be closer to this because the audio just doesn't pick up otherwise the way we have it set up. There's these other microphones. As far as I can tell, they're not connected to anything. Your team mentioned something like, wait, SGP graphics.c. We have no idea what that file is or why we have to modify that file. But that just got me thinking, is it possible to do this MP-1 assignment without touching the driver at all? And I think the answer might be maybe. I mean, it might be correct, right? That if you just assume hard-coded viewport parameters in viewport and some hard-coded like render output frame size and things like that in render output, you never swap buffers or anything like that. I guess you could probably get it to work without that. And that's why I mentioned that viewporting application would be a good, because that one I don't see how you get that one to work, where you're drawing custom-sized viewports. That one wouldn't work without some driver code to actually set the viewport. So with that said, please feel free to get started.
Cool. Yeah, so we'll go to you.
So here was our viewport design. So before we found out that we had to change SGP graphics, we thought the viewport was done, but there were a bunch of problems that I did when I wrote the VHDL code. So there was some math. It was really straightforward. The big thing that I did by accident was that I was sending data down M-axis T data. So it was sending data down onto like the master AXI bus, which was overriding everything down on the render output. And then
part of the, I'm just going to interrupt you there long. Part of the issue is just the naming convention, and I talked about that, right? Where like those first few letters in the signal name do tell you what you need to know. M for master, AXI, S for AXI stream, and then T data is just the data line on it. But the master slave or sender receiver terminology, initiator responder terminology, it's relative to something, and so it doesn't always necessarily tell you what is what just by seeing the M there. So something is the master and something is the slave, but it's a relative term, right? So you have an IP core that it's both, right? It's on the receiver side for one part of the transaction, and it's on the sender side. And I don't think there's a great shortcut to figure out what is what, other than looking at things like port direction, I guess. So M_AXIS_T data should have been the wrong direction port for you to send data on. It shouldn't have worked, I don't think, right? It should have been like a syntax or other kind of error.
it didn't throw any error when we wrote that in, so I thought it was fine, but then it was last night, and then we figured out that, it's not getting any data at all. So we went back to the viewport, and then we checked for debug, and there was a lot of stuff wrong. Like I was also sending the wrong T-last and T-ready signal down the line, so this held us up the most right here.
So if you want to output, just did the restart stuff, convert the K1616 values to integers for the color and the X-ray coordinates. Then the manager here is just having the colors wrong, and that just would change how it looked. So.
And just for future usage, I mean, you kind of wrote your own, but there were some helper functions defined that make some like the bit manipulation a little bit easier. And it looks like you did it yourself, which is fine.
Yeah.
But there was functions already that I provided that kind of, if you wanted to get the red color channel information, you could just call that function, which is just grabbing the same number of bits that you're grabbing there. So you re-implemented it, which is fine. It's not necessary either.
So for challenges, very close to the screen because I can't see. So we forgot about the SGP graphics, which was a fun old time to figure out. It was only 8 lines later, but it was a fun old time to figure that one out. We had some problems. So when we did the OpenGL application, it used the SGP none. And sometimes it would work for us, sometimes it wouldn't. It depended on what files got made. and sometimes the make didn't always make them all, so you had to do it a couple times before they would work. And then SGPE, as far as I know, it worked. And so yeah, so then when we were doing the OpenGL stuff, that was an interesting case. So with my OpenGL application, I'm going to skip down to results because, yes. So we started out with just looking at the examples and just kind of seeing like how to make an OpenGL application. So we started with like the dot, built from the dot, and then we built a line function so we can make a bunch of lines. We made them nice, so then we got a bunch of circles. And then to be even more creative, we decided the circles are going to be anywhere on that line. Why it's that line, I still don't know. But 7 circles of different colors will appear on that line of a different gradient. I wanted them to be different shades, but the manipulation took a little bit. So they're just white to whatever color they were supposed to be.
Is it a gradient? They almost look like there's like a lighting model you apply.
Yeah,
That's just gradient to white.
Yeah, it's a white bit. It starts out white because I have them all set to 1 for high. And then it subtracts whatever color you want to put in, which is randomly selected. And so what I wanted to do was do an operation that if the bit you're going to is lower than the one that was there, they have them both random, it would then have a gradient. It wasn't working in the time I had, so we just went with this. So it looks pretty nice. So then back to testing strategies, we use the VHDL test bench, a logic ILA, some handwritten calculations, and then lessons learned is Avado is finicky. Debug while bitstream generates was what we did a lot of the time because bitstream took about 20 minutes. And then for OpenGL, it was just, we were unsure how to kind of get data set at the beginning. It was kind of a process to get it going and then playing with functions as we went. Far away. That's all.
So if you go back to the viewport slide, so you didn't have viewport working until last night, is that correct?
Yes, and then we just had to remove that one m-axis t data where we're sending signal down onto that one particular port register, and then me and Joe, we recorrected how the TLAS and T-ready signal were getting catch and getting sent, and then we started working on that last bit stream before I left.
That's nice that it worked, I guess. So to go back to the SGP graphics slide, you had a screenshot of code there, which is fine. I can't super read it here. And no one got labeled as doing the driver changes here. So who figured this out? What is this driver change doing particularly?
I think here they're just switching the back buffer and front buffer, but Joe and
so
Diane
does the buffer switch and then flush the cache, wait for it to actually flush, and just sets it back to what it was configured to before.
Other teams can tell me because now I don't remember MP-1 design exactly how I said it. Is that cache config, is that already set in the core that you could flush the cache by just setting a register? Oh, that was nice of you. Okay. Part of me wanted you to figure that out yourself and come up with some control for it. Okay, so that flushes the cache, and there may be some status bit to read to confirm that the cache is done flushing. Did anyone else figure that out, or did you just did a micro sleep of enough time? That's probably okay. I mean, everything's going to be pretty slow as is. That adds a decent amount of latency, right, to every frame. And then you write, don't cache anymore, don't flush anymore to the very end. You also need to make changes related to viewport. So that would be the other thing to look at while you're working on other things tomorrow, that when you get a call to like GL viewport, which has like the X and Y limits to them, you just pass those in registers. And then
we did that as well. We just didn't take a screenshot of it.
Okay, so that's in the driver
Yeah.
as well. Okay. Any other questions for group 2?
And if we observe the test bench, there is one thing we observed it.
The way.
Huh?
That way.
Oh,
There you go.
So that's simulation. That's very nice looking simulation at least.
So these are the output one. This is 64-bit format. This is 32-bit format.
You'll have to speak up a little bit.
Oh, sorry.
Speak a little.
The YVP value is off by 1%, but when we looked into the entire design where the value is going off, we found it's due to the multiplication operator. The value is off by 1, hexadecimal 1. So, but still it worked, so it's like we aren't corrected.
Might be a bug. So like if
So because the XVP and YVP had the same math applied to it,
right,
so but the only thing different is the width and the height.
right.
So with that particular value of height, the value is getting off by 1, maybe due to the correction because the multiplication algorithm is implemented by the tool since we are just giving
But I would trust the tools to do the multiplication. I would trust if you have like the multiplier operator. I think it's fair to assume that you'll get like the correct result for doing the multiplication back out. I think that's okay. It's just off by 1 line.
But we got proper output, so I was like, okay, if it's working then.
Part of the issue though, so that's fine. It's depending on what you're testing. Off by 1 errors in things like the Y dimension might be really hard to see. So it may still be a bug. Even like a couple of the applications that fill the whole screen, like did you ever run that fractals application on the board? That was the nice one, I don't know. Okay, but even if you were off by 1 and it was like overlapping Y, like it was, what was on the bottom was now on the top, there's a lot of symmetry in that pattern. You may not even notice that it happened and it's like 1 line of pixels. You'd have to really be staring at the screen. And for like the planets one, if it's just one thing, if you didn't have a planet of a totally different color, you may not have even noticed it, or it may not have looked like much. When I talk about technical debt, that kind of thing may still be an issue here. At some point, it's fine. They're all going to look kind of janky at the end of the semester anyway. But like, okay, you just take a note of, hey, there may still be something here with our math or our understanding of viewport. Let's just tag that as a potential issue. If later in our triangle you see the bottom row of the triangle, and there it will be more obvious, I think. You have this triangle that takes up the whole window. The bottom row of the triangle is actually being displayed at the very top. Maybe your rasterization algorithm is actually perfectly fine. Maybe viewport's the problem then at that point. And if that's the case, then that's going to be perfectly fine. But that's for every team, you know. Don't assume that MP-1, just because you get full marks for it, that it's like perfect and working. Assume there may still be some issues with it that you could go back to, you know, for MP2. That's okay. Awesome. Okay. Good job, team. Group 3, you're up. 2/3 of group 3 is up. I have questions already. Not gonna pick on you guys.
I did a lot of stuff.
So, okay, hardware is like all of it, right? Okay, 'cause that's also driver stuff as well then? Okay. OpenG application is fine, 'cause that's very important. Contribute to the lab report, you know, everyone should be kind of doing, it's not a technical contribution. So, try to find ways to collaborate a little bit more closely on things, because as projects build up the technical debt, like individuals also build up technical debt in terms of like your understanding of the system as well, that if you don't really understand MP1, MP2 is going to be really complicated, right? So it could be worth it on Wednesday that after everyone's already looked at the MP2 report and you kind of understand the 3 labs, like, hey, let's all make sure we all understand MP1 as well, that like, here's what we wrote in this file and why, here's how I test this and why, and here's how it all comes together and why, but that's fine. You can also do a solo run if you want to try that as well. So here we go.
So here's our finite state machines for our render output and viewport. The render output one's missing the back arrow, but they're simple enough. I think they're pretty much the same for everyone. Yeah. I wrote some. Yeah, our render output. Yeah, I'll talk about that in the challenges. But so here's our viewport code. We what do I talk about? Okay, so.
Why don't you walk through it? So these are the
Yeah.
states. I think I might have provided the names of the states for you. You didn't have to use them, but you're
Yeah,
pretty
these are-
safeguard to use them.
This is our finite state machine. We wait for our vertex, and then we calculate our x values, then we calculate our y values. We could do that in the same state, but it was already split. I should probably combine them into the same state so it's faster. But and we calculate our EP coordinates. Or we assign the VP coordinates and calculate Y mult and calculate X mult. We just use the equation on the lab report or on the lab. And the render output code's a little bit more fun. So we generate our address. We had some issues at the very end where we were getting lines in our like large.
Is it on the right-hand side?
On the right-hand side, and it's because we weren't rounding our positions correctly, and then that fixed it. And then, we just assign all of our colors. I think you said you had a function to do that. 39 down to 32 worked. That's what I did. And we generated our frag address, which was really fun to write. It's cut off because it was so long. I'm sure I could split it up, but you can't.
The problem with that is it's a lot of lines. That's fine, but and hard to debug it, right?
It is hard to debug it.
Only thing I would suggest to people would be, of course, ask the TA is fine for something like that, or ask me. But does the address that gets generated in simulation, does it make sense? Is it in the right rough order of magnitude? Knowing that it's exactly correct, I think, is a little tricky because you can only simulate so many points. But is it in the right frame buffer at least? Is the least you can check to see? Okay, I know at least a fragment or a pixel is going to get written somewhere in the frame buffer. That's one thing you could have tested.
So I have a quick question.
Yeah.
Did you meet timing on the first try with it like this?
No, I did something. Yeah, so you can see the mem total variable up here. This was to multiply the stride output height and the stride output stride. Because when I had that in one line down here, it didn't meet timing. So I just moved part of the calculation to the previous state.
Some people just hard code. And I was thinking about that. And I don't think it matters for us. I mean, conceptually it does matter, right? You do need to be able to support different rendered size targets and things like that. But for the HDMI, the monitor, everything, I think it's always going to be 1920 by 1080. So if other groups, if this still becomes an issue, the driver technically sets some registers for stuff like that, you probably are okay. Just hard coding it, and that could save a multiple.
So we had to make 3 driver changes. We swapped the buffers up here. Just do your right to the buffer, or right to the register. Then we flush our cache. The other team did it differently because I did a read to the cache so that when we board it, we made sure that we kept the pre-existing things inside of the cache control. And then I wrote again and I got rid of the flush using some bitwise operations. Yeah. And then setting the viewport params was easy enough. It's just I missed that the first time, so it took some debugging because I didn't know I needed to do that.
The other thing that seems to catch a lot of teams, and it's fine. Maybe the makefile should check for the staleness of the drive, but usually when you make an application, it doesn't check for freshness of the linked libraries. But we have to. So every time you make any change here, you have to remake the library and then you remake your applications. Actually, either order is fine, but you don't run your applications. A lot of teams, I think, never hit make on the driver and then it was working, but they didn't realize it was working until.
Okay, so here's our whole list of challenges. Everything. So, forgot to offset the viewport. I didn't actually notice anything wrong when I didn't do that. I just changed it at the end because that's what I could have done. Rounding pixel mem address, I was talking about those lines before. It's RBG in the memory instead of RGB? Maybe. Or maybe I just
Somewhere I have wires screwed up in the system. So let's go with that. Because now that you fixed it, you don't have to change it again. It's done, right? So, okay, you got your blue and your green swap. You're good. Okay.
My linter stopped working at some point. So it kind of relied on synthesis for syntax errors, which was a bad idea. The FPGA has to be reprogrammed sometimes for it to actually work. And I didn't do enough simulations. I should have simulated more.
And that second last bullet, the last bullet point's also very valid. But the second last one, I think we'll find that unless your design state is perfect. That, like when you hit quit on your OpenGL application, your FPGA is in perfect state. I think that'll be common for a lot of teams. That you want to try 3 different OpenGL applications, for now you may find yourself reprogramming the board each time between them. And I think that's not what I expect to be the case, but I think that's pretty common that something gets in a weird state and you have to reprogram each time.
Okay, so here's all of our results. They're all fine, I think. Like, one thing I noticed is the Sierpinski's triangle. It goes to the very top of the screen, which is weird. That makes me think there's something wrong with my viewport. I just noticed that this morning.
I think there may be something else. So a couple of these applications have different sized windows. So some of them, like the Frax, I think is by 1024 and not by 1080. Sometimes the issue is also, it gets a little subtle, where like if you open up an OpenGL window in GLFW, you specify a resolution. It depends on the resolution that your windowing system provides. It needs to provide some pixels for like the menu bar and things like that. So you may not always get what you expect, but Dr. Jones's head looks cut off from that.
That's how it was in the like window that popped up next to it too.
Okay, so in the actual OpenGL app.
Yeah, so that's how it is. I wish his face was there, but it's not. It is.
It's on the middle.
But yeah, the Sierpinski's triangle, it's weird. It goes to the very top, which I don't actually know how it's doing that because the memory isn't big enough to do that. But like it should be going into the other buffer instead of going to the very top. I don't know how that works because the screens are 1920 by 1200. I don't know.
Oh, they are. The monitors.
Yeah, the monitors are 1920 by 1200.
Well, okay, that's interesting. They weren't last year, so those are new monitors. So, but I think they probably can support a 1920 by 1080 resolution, because that's up to the. You look too tired to have that discussion right now, which is fine. That's up to like HDMI like negotiation, right? So they may be 1920 by 1200 when like nothing is plugged in or when like the workstation is plugged in. But then when the FPGA board, the simple graphics processor design says, hey, I'm sending you HDMI data, they should switch. They should switch to whatever we tell them to switch to if it can support it. So I think that might be okay.
Then yeah, the fractals work. They're fun, they look cool.
The Fern was written by Dr. Matt Weinborg when he was an undergraduate student here.
Really?
Many, many years ago. I don't remember how many years ago now.
Oh yeah, so Sid can talk about his OpenGL application.
Yeah, that video you just saw was the program. It's basically, I tried to make this like rainbow pattern using just the RGB values. You can see it starts incrementing between red, bring blue, green, red down, move, red back, and creates the colors of the rainbow. I noticed that when I was testing. I was like, I wanted to use that. So the program basically, this is like a simplistic, just 1.5s, but it's a full linear transition between each one. And then I used shift on the process to make it actually scroll up the screen, which
It's probably still be pretty slow. But
it is.
Pixels,
It is slow on the FPGA.
It's like pixel move.
Yeah, very
10
slow.
seconds.
It was just fun to make though. And when you run it on the, this is on the, this is on the, just running it normally. You can see it on the left there, that's on the actual FPGA. And obviously it's not gonna be very animated. The video would take a while to watch.
I'm doing time lapse, but
Yeah.
Noise just speed it up, I guess. We don't normally want to send, I mean, we do it for this, and we don't normally want to send a whole like screen
Yeah.
full of pixels of points as pixels. So, but it's pretty cool. Any questions? Way to go. Great job. Group 4, come on up.
Okay, who wants to drive? Okay, I'll drive.
Sounds good.
Hi, everybody. I did the viewport. I'm Will, in case you forgot who I am. James did render output, and Brandon did OpenGL and all the driver stuff. And then we all sat down together to debug each other's code. So for what I did, it's the same diagram everyone else did. The state machine given the states that Dr. Zambrino gave for us. The only difference is that I used curvy lines on my diagram.
I opted for the straight lines.
Exactly.
I don't know, does it say anything about your respective personality?
Maybe, actually. Yeah, you're onto something. The render output is pretty straightforward. We actually ended up adding an extra state in between generate address and write address, just with the way that processes work in VHDL. And that's something I learned a lot this lab. That was a big struggle.
Cool. I guess I'm also missing on the vertex write return to wait for vertex needs a call out for the condition there, but
So for the drivers, I read a comment in the GLX swap buffers function about waiting for stuff to finish in the status register. So I wrote that whole while loop there to wait for everything, and it worked on my
Is that in the upper
workstation.
left-hand corner? I can't.
Yeah, the top
I'll take your
left
word.
there. It worked on my workstation and my FPGA. It did not work on his, so we just commented that out for now, and it seemed to work just fine.
And I'm gonna just interrupt you briefly, because I like the idea. The issue, I think I might have mentioned it very briefly in class, but I think it was before we even really started on this in earnest. It's not that obvious when the pipeline's done. There is like a T-last signal, which should be for the last primitive in a bunch, should get set. Vertex fetch, that module should be sending a T-last signal. So you could connect that to a status register and check to see if that's gone high or not. What are you, in these while loops, what are you polling, or what are you reading from these while loops?
I'm reading from the graphics map. I looked at the graphics map structure, and there was a status register field, so I was just looping through all of them and checking for the status register to see if it was done.
So for vertex fetch, that's probably fine. But for the other two IP cores, you would have had to add that bit in the status register to like confirm that it's not busy or not working.
That would explain why it didn't work.
Yeah, that would, so it's one of those things that, it's funny, it might like accidentally work sometimes, but I don't think this is, at least the way we've designed, I don't think it's that easily to solve it. Something like that I think would make sense, like check every core and see if they're all like done. And you may want to add that to the other two cores. That'd be pretty straightforward. When you're in, if you go back a slide, when you're in state, wait for vertex and wait for fragment, set that status bit to ready or whatever, or done or something, because it is done when it's in that state, right? But I think the issue is you also have these FIFOs between these components, and there's no guarantee which of the IP cores are done in which order. So I don't think it's as straightforward as saying, oh, all three are done, the whole system is done. The implementation I've seen like checks it in reverse order, and then checks it again checks it twice, and that seemed to kind of work. But you'll see that in MP2. So we talk about like technical debt. You'll see in MP2 where your triangle is going to look kind of glitchy because it's not clear when it should swap buffers. And so some hooks there is a good starting point, I guess, is what I would say.
And then the rest of it was pretty straightforward. I did forget to do the cache, so we were getting a bit of weird flickering last night, but just added the cache flush, and that fixed that immediately. And yeah, that's pretty much it there.
Things we suffered, had a bad time with. General Vivado rage, just kind of quits all the time. It crashes.
I'm going to stop you too. So is that happening to everyone? When does it crash? What are you working on when it crashes?
It crashed for me like every time I like repackaged a core and had to like regenerate the output products.
I think it happened a lot. Weirdly enough, we would get seg faults on syntax errors, which I feel like there's probably a better way to compile our hardware. But like, if we didn't compile it properly and still tried to push it,
Add implementation crashed a lot.
yeah.
So I asked that because I've switched almost entirely. It seems it's very backwards. I've switched almost entirely to using Windows systems for Vivado. And so I haven't seen the crash. So for me, at least, do you use it on Windows also, Ben, or do you mostly just Linux when you're using Vivado?
In the past, I've used it mostly on Windows, but for this class, I've used it on Linux.
So we can't switch the we can't switch those computers to Windows at all. But you may find that, just having it locally installed and just running it if you have a Windows laptop may be better. Because it's not, every piece of software crashing, it's not supposed to crash like every time or crash more frequently than it doesn't. So maybe I'd like to visit the lab and like see it in action, see it crashing a few times.
We'll start making tallies on the whiteboard.
Yeah, that would be fine. Because that's not supposed to be like the pain point of the lab, but like the software is terrible. It's actually a very good piece of software. Maybe there's something we installed and configured wrong, or who knows.
It's much better than designing the whole thing by hand.
Well, that's right. We don't have an alternative, obviously, but Windows would be one alternative, just to give an example. So I at least personally had it in a state where I felt you did have to click things in the right order, like packaging IP core. You had to make sure you had that in the right order, and then things were pretty stable. So anyway, we can monitor that and see if there's some workaround we need to apply for everybody.
So in render output, firstly, actually before those 2 points, I've only really ever worked in like structural VHDL. So working in a process was like, I actually had to learn the syntax and like the do's and don'ts. I didn't realize you couldn't use and assign the same signal and like the same process clock or whatever. So that was a big pain point. We also realized that our color was backwards and kind of mixed up. And we also ended up doing the blue before green. And then our address calculated mapped to memory wrong. I totally implemented it thinking memory was in like the top left corner. Even the lab said that wasn't right. I kind of looked over that. We also added a 4 times overscaling in render output, which made our outputs really weird looking and like overlapping.
It's very tall.
Yeah, very tall. Our Sierpinski's was like super weird, and we have a video on the next slide for it.
One team changed it. Was that your team that changed the driver to get rid of the 4x4 stride length?
Probably.
Was that and then did it in hardware instead? That was your team.
Yeah. Anyways, cache flush. Oh, I still can't get mine to like work, which is kind of annoying.
James is cursed. I don't know.
I have a
what's
window
wrong.
coming up, and I have like some pixels on the side, but I can't, like both of them can get it, and for some reason mine, I think I might just have to like reclone and start from scratch. But yeah.
How's the team doing on like sharing code? Like, is Git working well enough for the team?
Yeah, it gets fine. So.
It's wonderful. I think I don't know what's wrong with
Something's
James.
up, so
We get
I don't know.
or his current clone.
That's the funny thing with these projects. You're writing very little code, right?
Right,
In
it's
terms
like
of
a couple
in terms of like
files.
the diffs between your version and his, it's very little, but like all the tools have to be exactly in the right configuration. The one gotcha I mentioned before is always a very common factor, and people don't believe me until they try. You have to rebuild the library and then confirm that like, the changes are in place there, and it's easy to forget that.
Next. Oh, here's our fun video of it overscaling, and then there's also the fuzzy part because we didn't have our caches working, or our cache flush working. So you can see that it's like twice as tall as it's supposed to be, and so it wraps, and then it kind of just pulses in and out, which is kind of fun.
We were
Um,
mind boggled.
It's all better now, but it wasn't before. But yeah, everything works. It's wonderful, it's pretty, it's gorgeous. We got our beautiful Mandelbrot and Sierpinski and the weird brick texture.
Oh, yeah. For our custom OpenGL application, I just made a snowman. I was doing all this remotely over the weekend, and I was having issues with the remote desktop. So what I had to do is I had to clone it on my desktop machine at home to get it to actually compile and work. So it was a bit of a struggle, but I wrote a function that takes a slice of our pixel array and generates a circle in that slice. So I could just call the generate circle function 3 different times to make our little snowman here.
Going forward, I think we could go back and change the OpenGL program to add like a little nose and like a cowboy hat. I think that would be nice. Those are my only complaints about the snowman.
Very
That's
cool. So good job overcoming. If you go back to that video of the Sierpinski, I mean, that's. So first, when you get that, you know, hey, things are close, right? So that's not a terrible feeling, right? It's like, okay, you know, we're close, we have something green, and that's tricky though. So seeing like, so that's frame to frame is what I think you're seeing, right?
I think so. Yeah, it's the two buffers.
It's the two buffers is what you're seeing,
Mhm.
maybe.
So that was before we fixed our memory address calculation. We were doing it entirely wrong. We weren't looking at like several of the different variables.
Yeah, it's not. But that's the thing, though, right? It's not that wrong. You know, it's not that far off, right? If it was random green pixels, I'd say, okay, you have something, but render output has got the wrong address calculation. So it was off by some constant factor in the y dimension, I guess.
Mhm.
I think we were using the hard-coded stride length
Yeah.
that was already multiplied by 4, and then we were multiplying it by 4 again. So I think that's why it was so tall.
Yeah, and although I know you got rid of it, or some got rid of it in the driver, I feel like let the driver do as much work as it can, because then that's less like VHDL, less things to have to fit on the FPGA board. So let the driver do any pre-calculation it can do, and then minimize the amount of hardware work you have to do. But that's pretty cool. So for future ones, I'd like every team to try to record interesting looking like fails along the way. So just don't forget, oh, okay, you know, blank screens are interesting, but something that like, you know, like that, please do feel free to record those and just have those handy, because I think that'll make for a nicer story like this is of like things that you overcome along the way.
We tried to get this video 4 different times, and every time I pulled out my phone, Brandon closed the program. So that was fun.
And I do understand though that, you know, there's multiple reasons, the genesis for a bug, so you can't always obviously say, yeah, we fixed this one thing and then this bug went away, but still seeing it along the way, I think makes for an interesting story. So, thanks team, great job. Last but certainly not least, group number 1.
Does someone really want to do the slides? Otherwise, I can.
I can do it.
Okay.
Yeah, so I worked on some of the viewport and driver code, and then I ended up being sick, so missed the whole essential part of the week. Okay. Oh, we're not gonna do. Okay.
Well, I was working on the viewport and driver code also. I helped Ben with some of the system debugging. I'm Andrew.
Yeah, so I did the render stuff and then trying to put it all together with Andrew, like you said.
And I did the OpenGL test application.
Yeah, so for the driver code, we actually ended up changing 3 of the functions. So this is where I took out the ×4 from the assigning the stride to the render output in like the init function. But we might end up moving that, I guess, back to the driver.
If it's
in
×4
the future.
and not required a multiplier then, right? It's just
Yeah.
probably shifting
He
it
just
over
did
by,
like a shift left
So-
by 2, so.
yeah, or just taking the bits, right, basically, so there's no harm.
Yeah.
There's no harm. As long as you remember that, right, because your code's always gonna look a little bit different than everyone else's for that part, but sure.
Yeah, and then we also added in the swap buffers, so just switching between the back buffer and the front buffer for render output, and we added the flushing the cache also. And then in the viewport function, we just assigned the registers. And for a while, actually, like the make file, it defaults the path into like the SGP folder, and I was working in like a copy of that. And so I was wondering why none of the changes were actually working, and then I added in like a version number thing, and it wasn't printing out. So then I finally figured out it wasn't doing anything, which was annoying. But.
For the viewport, it was just the basic FSM design, doing the transformation. Yeah, I don't think we had any issues with it, because it was fairly straightforward when we did simulation, but when we were connecting it to the render output, we had a bit of issues.
We have curvy and straight lines in the FSM.
I saw that.
Yeah, and so then for the render output, obviously that's just calculating like the color, the actual pixel value, and the address. So this is the code for the color calculation.
And then this would be the address calculation. So the design, the render output core, it like failed to meet timing the first time I synthesized it. So I actually had to like add some like intermediate states between like the start and the gen address to do it like one step in each clock cycle to get it to meet timing. So those like commented outlines there, they do still take place, but they each have their own like state and register in the FSM.
So you have like the data flow, but they're not actually directly connected to each other, right? There's another register you defined it in the state machine to connect results. Yeah.
Yeah.
Very common. And I was mentioning that for MP2, I don't think teams will run into timing issues. But the flip side is it's very structured for it. You have to kind of follow the recipe for MP2, and if you do, I don't think you'll. If you try to just be very creative with your VHDL, you'll run into troubles. But if you just follow, here's a starting structure and just use this, then you'll be fine with timing for MP2.
Okay. So I can do the bugs because that's more or less just a continuation of the render output. Did like everything possible wrong when making render output the first time. So after we ran down all of that, it worked. And so they did a good job making the viewport. I just messed up big time on the render output. So
converting color to 8 bits, a lot of teams used to do like times 256, but that would be wrong, right? Or what was your converting to 8-bit color around?
I think I was multiplying by 255 after like truncating the part that stored like all but like the most significant bit of the color value. So like the color would show up if it was a perfect 1.0 in the OpenGL, but all of like the partial colors were just getting thrown out.
And eventually, there's a couple applications where we talk about how like, the color values are 0 to 1, or these normalized values. But some of the OpenGL applications will actually specify 1.5 for red. And you may want to go back, since you've done that, go back and look at render output and say, well, if it's greater than 1, just flush it to 1 and then do the rest of your math, and the color will look pretty good. But that'll be in a few weeks. Then you'll see a couple of those applications.
Sure. Okay, so yeah, that's what the output looks like for the Sierpinski and Fractal ones.
How did you get such nice, or those, I can't tell, those are pictures from the screen, I think, right?
Those are like the images of, those are like the frame buffer, when you do like the SGP, FB transmit, and then it.
You should share your knowledge with the rest of the class about that, right?
So there is a command you can use to copy the frame buffer contents to the directory. I just always run it in the directory with the, like where you make the applications, like the number and then the name. So you just type like SGP _ FB transmit -R, and it copies a bitmap image into the folder. So then you just click on that and it opens it with whatever the default like image viewing software is. So that's what those screenshots are from.
Yeah. It's pretty helpful to see the color of like one pixel, because I think there was one we thought was black at first and it was actually blue.
Yeah.
Awesome. Did I not mention it? So that's the application I want a team to use, but I may have forgotten to mention it. How did you?
I think I was like the only person that watched the video on Discord.
Okay. All right.
So then we have a video of the test application working. It did a really bad job capturing like the actual. It is on the FPGA monitor on the right. It's just
you can maximize it, but there's also no need. I'm going to say why in a second. I'll pick on the group or anyone. Why do you think we're having trouble seeing Stickman here? Nothing wrong with the application. It looks wonderful. Nothing at all about quality of the application whatsoever. Why can't we see poor Stickman?
Oh, there it is.
Yeah, okay, you can kind of see it. If we go back a few seconds in the video, why can we not see Stickman?
Well, I think the application uses the big points shader. And
Sure, that's definitely part of it. Why can't we see like regular points from this distance? Someone tell me.
It's a pixel.
It's a pixel. That's correct. What resolution is this video that's being taken?
Probably less than the screen.
I think it's 1080. Well, of course, if it gets uploaded in YouTube, codes, transcodes, does all sorts of stuff to it. But even assuming it was like perfect camera output, probably 1080p. Probably that kind of high definition 4 megapixel camera sensor, and you're pointing it at a 1080p monitor then too, right? From a distance. So it's a fundamental aliasing problem. You're never gonna be able to see a single pixel from a distance when you're recording it, on a monitor like that. So I guess when zoomed in, you could kind of see it,
Yeah.
because then at least you're zoomed in quite a bit, and it's not the full monitor you're looking at any given time. So you showed again, though. So I was so focused on that, I didn't look at what Stickman was doing.
So he actually does run, and Maisie set it up where if you press the space bar, he jumps. So that's pretty cool when you can see him. He comes equipped with urban
There he
camouflage.
goes. There he goes.
Much
Well,
faster.
blue on blue was a choice. Okay. It's getting
When
there.
it's not running with the board, it's a lot faster.
Sure.
So,
He goes from like a sprint to like a leisurely jog or stroll.
So you're another team that did your own, basically line rasterization algorithm. So there was all the circle groups, you also did basically a circle, and which group did the other lines? There's another group that did lines, I thought, or at least did the color. That was basically, you're doing it row by row, right? Yeah, those are horizontal lines, I guess. So we're going to cover that next in class. Maybe it's obvious. Well, the truth is there's a naive way to do it that works, but then it gets harder and harder for different circumstances. So we'll learn next about line rasterization and then apply that to triangle rasterization, which is really just one way you can rasterize a triangle. Effectively, what we are doing in this class is those 3 points, you worry about the lines, and then you do line scans, and you're basically just rasterizing lines from one edge of the triangle to the other edge of the triangle. So while we don't do a lot of lines in our applications, because you can only do so much with lines, the same algorithms apply for doing triangle rasterization. That's what you're looking at for the pre-lab for tomorrow. It may not seem that obvious that that's what you're doing, but we'll talk about it in class, and we'll learn more about it in class, and that's basically what we're doing. We're setting up the parameters of a triangle, so we basically know where the edges are and what the derivative is, what the gradient is from the various edges, and then we're just going line by line and figuring out what the value should be, like what you're doing with that particular stickman that you have there. So, any questions for group number 1? Okay, congrats team, you did it. Okay, I think it's reasonable for us to kind of call it a day today. Great work on that. Again, I'll just repeat it one more time. Take a little break, but then take a look at MP2 and read through it. Watch the video, that would also be useful. So Ben gets bonus points for watching the video that I made for that. Try to do your best with it. It's not as, you don't have to completely master the pre-lab for MP2 to be able to get started on MP2. You'll be doing a lot more reading of code than writing of code also in MP2, I think, as well. It is going to be a debugging lab very much. So those skills that you've started to develop in understanding simulation are good. That next step of debugging, I didn't get the impression that any team had to do this yet. Did anyone use the ILA yet and try to connect? Okay, that's pretty necessary, I think, for this level of debugging. The difference, though, is that while render output was very hard to simulate, we should be able to simulate this triangle rasterization pretty well. The only issue is, it depends on the size of the triangle, how much things you want to simulate. But some combination of just pencil and paper working through the algorithm, doing simulation, and then doing live debugging using the ILA, you'll get past MP2 and you'll be able to get it done. But with the caveat that for I see at least one of the teams, but I think possibly 2 of you, there's some bugs you probably have there that you didn't see yet that will come out now in MP2, and that's okay. You'll look back at the MP-1 code and you'll say, oh, that was really straightforward. Why did it take us 2 weeks to figure this out? And you'll need to solve a couple more bugs and overcome a couple things to get it working. But this was really great. So I'm excited to see what you have coming next. And the lecture and the lab content is going to be pretty much synchronized for the next couple of weeks, and that'll work pretty well for us. So let's leave things here as a class for today, and I'll see everyone in lab tomorrow and then on Thursday. Thank you.